My name's Daniel, and I'm one of the co-authors of Raptor, a fully autonomous offensive and defensive research framework. And we kind of built it because I guess all of us have run some form of security scanner over the decades and ended up with thousands, if not hundreds, if not tens of thousands of findings back. And we're left with the question of like, do we triage them all? Do we fix them? How do we fix them? I guess that's kind of where we decided to leverage the power of large language models, but also try and build something that was pretty unique. So for this test, I decided to revisit a very old version of Apache HTTP. 2.0.35 was released on the 5th of April in 2002, and I decided to throw Raptor at it as an example. This has been powering web servers since, a very long time. And what we got back was pretty much standard as you expect, 606 raw findings. We did have one critical, a CVSS 010. And as a result of this running for a good couple of hours, we ended up with 2 working exploits. Now I wanted to step back and kind of go through why and how it all works. But first up, Raptor kind of finds the stuff that's been buried. And I think for anybody who's been involved in vuln discovery and vuln research, a lot of your time is spent digging through dead ends, going through rabbit holes and so on. And that's kind of why we built Raptor. So I guess first up, security tooling has a bit of a signal problem, right? What scanners do really well at the moment is they find patterns that look like vulnerabilities. They are very good at covering the code base systematically. And, they do so in a fast way that can fit into a pipeline. They give you SARF output, they tick compliance boxes, like generally they're pretty good. But what they can't tell you is where we've started to explore is this actually exploitable, right? Or is it dead code? Tell me more about the attack path from the source, the sink, the data flow. And for somebody who's responsible for fixing the bugs, like if I take those 6 from the 6 findings, like how do I ship a fix today? How do I ship a fix in the next hour? So a lot of people can't answer those questions. And it's not because they're bad at security, it's because, often you need somebody who spent years and years looking at GDP outputs and crash traces and understanding the flow. And it's a hard task, right? And I think Raptor was built to try and attempt to close that gap. So why did we build it? I guess, like I said before, we wanted to make it so that people could find bugs a lot easier and leverage the power of large language models. And indeed, frontier models today are utterly fantastic at this, right? So, you don't necessarily need to know which of the 606 findings will kind of need your attention, right? Raptor helps with that. And like I said, large language models really kind of gave us this reasoning layer on top of some of the most amazing tools that you have at the moment, SAMgrep, CodeQL, AFL, etc. Right? It does all the triage work. It does all the heavy lifting for you. And it's the same kind of analysis that a security, senior researcher would have. And more importantly, finding the bug is only half the job, right? We didn't just want to build Raptor so that, it found vulnerability and it wrote you a working POC. We wanted to kind of give back. We wanted the ability to have people create patches, right? So it takes a confirmed finding and more importantly, writes you a fix. So if you're testing this on open source projects and open source maintainers would benefit from this, like explains why it was wrong, what was wrong, and how do you fix it? And I think that's really important in this day and age where we've got so many bugs being found and not enough fixes. And finally, a big part of our philosophy was that it should be open source. It shouldn't cost hundreds of thousands of pounds a year or cost in headcount or so on. Like I think everybody should have access to such a tool. Like most tools kind of just hand you a problem and walk away, and we didn't want that with Raptor. So let's have a look at the pipeline. And the pipeline is really important for Raptor. The first up is you give it either some source code, ideal, a binary, or a repository, or something that it has to look into and get stuff into. It then has the scan layer, and this is where you can configure it to use a variety of scanning tools. So if it's a binary, it can be AFL fuzzer, or source code, it's got SAMgrep and CodeQL, 2 phenomenally powerful static analysis frameworks. And this is where the cool stuff comes. Raptor has an understand layer, and what this does is from that scanning and the understanding, it extracts really important information. Entry points, the flows, the sinks, the full analysis. What is it? How does it work? What does it look like? What do I understand there? And that passes itself into the reasoning layer. Like this is our secret sauce, right? There's a 8-stage mechanical validation pipeline where it really goes through and says, okay, you think there's a vulnerability there? Well, I'm going to argue with myself. Why is this not a vulnerability? Is this a vulnerable because it's reachable? Actually, it's not even vulnerable. Well, when it's compiled in a system, it's got these other protections in place. And it constantly battles itself to make sure that from each of the stages, when you do get a finding and it has been confirmed, everybody's happy. And for me, that's the really cool part, that exploitability validation. Is this real or is it noise? And, we've seen in the last couple of weeks a lot of people pushing up bugs that large language models have found. And they say, oh, it's definitely a serious bug. But the reality is sometimes when you look into those bugs, you've turned off all the protections, right? You've stripped it down to being the bare minimum. Or it possibly is a small denial of service that the reality is really hard to get hold of. Our exploitability validation field and validation thing there is really, really important. And then finally, the output. And the output could be your SARA file, so it fits into your pipeline. It could be a proof of concept exploit code. It could be a patch. It could be a report, something that's usable and tangible for you. So kind of most scanners do stop that. They give you a SARA file and say, hey, crack on, good luck, off you go, right? What we wanted to do was give people the power. So we give you the attack surface mapping, validation of each finding, the full tracing from source to sink, like all that kind of stuff. So you are far better armed at understanding what it is actually you're looking at. So let's look at Apache HTTP 2.035. It's 24 years old now, so I'm sure there's lots of bugs. And yeah, there were, right? 606 raw findings. Now, Raptor did validate 2 of them and said there was 1 exploitable with a CVSS of 10. Okay, great. And for heart of our concept, we've got a project capability that really shows you what the project was. So 606 vulnerabilities and 1 exploitable, like we need to break that down a little bit. So this is why people stopped looking. Some of the vulnerabilities it found was, first up, a vulnerability for a BOS module, which was really interesting because there's been 0 installs since 2003. BOS was a phenomenal desktop. I actually had one, but let's be brutally honest, this code hasn't been compiled in a production system in many decades, right? So what do you do with that? You don't do anything with that. The next one, shock horror. They didn't use TLS. Newsflash, we didn't actually use TLS back in the day, right? So there it correctly did say, hey, there's a plain text HTTP link, right, to Siemens.de, right? It uses HTTP. The reality is, yes, it's a security finding, but look at the context here. It's an old code base. It doesn't really matter. It's from 2002, right? Real vulnerabilities here truly do hide in lists like this, and it's time consuming, right? So with that Raptor, you're triaging by hand. I think this is where we've really tried to help. So the first thing we wanted to do was map the attack surface, right? We're really keen on entry points, all unauthenticated entry points. Like, where does stuff come in and what can you do with it? And we came up with 4, right? Naturally, request line, headers, chunk body, and content length body. It is a web server. That's what it does, right? Now, you'll notice there we flagged the EPO 003 chunk body. There could be something interesting. We then looked at trust boundaries, right? So what controls are in place? Well, we've got a request line limit, we've got a chunk line with a max value, and then the content length thing saying digit only validated. Great. But what about our sinks, right? Where are the interesting things that we want to look for? And Raptor correctly found that, hey, something pretty cool is going on line 1619. It looks like a shift overflow, right? There's some other things like shell exec and a buffer right? But that's the bits that we're interested in. And it finally says, okay, actually the one that we're going to go down is EPO3, right? It directly reaches the shift overflow sink at 1619 with no auth and no rate limit. And that's where we kick into the validate phase. And it goes through and says, well, actually, let's look into this. So it finds it that, right? The function get chunk size, which is a CWE190. So background is CWE190 is an integer overflow, right? Number too large, gets data type and wraps around, etc. And what Rat found during the validate phase was that chunked HTTP body sends data in pieces, right? When the total size is known up front. And this is where the vulnerabilities really starts to play. So if you look at here in the code, you can actually see this is the line. You're like, okay, interesting. But it's definitely exploitable, all right? It's given a CVSS 10, right? And it doesn't need an auth. Great, okay? Now, 2 attack paths came out of this, all right? So this is really interesting. And this is where the proof of concept came in, right? First up, let's crash the worker, right? Send a very simple post request, lots of eth. What happens? Okay, well, it goes in. You can see the code that happened on the previous slide, right? The worker aborts. If you do more than 20, you get memory exhaustion and it falls over. Boom, crash confirmed. Great. Okay, so that's a DOS, right? Which is pretty bad. Right, now, obviously, Apache prefork does respawn newer dead workers. Great. But if you keep on adding that up, you just exhaust the pool and the server stops accepting connections. That's pretty bad. Okay. But here's an idea. What happens if you inject a second request using the same connection? All right. So we send one TCP write and we send another. And you start getting lots and lots of data. It hits the overflow, which wraps to 0. And then basically the fun starts to happen. And if you look at the exploit the Raptor managed to create, you can start to see here, something has really gone wrong. So 2 HTTP responses and 1 connection. The server correctly dispatched our injected request internally. The method path and headers are all fully attacker controlled. Great. Happy days, right? There were other vulnerabilities, and it proves here that actually this one didn't work, right? And I think this is where the validate function really, really works well, okay? We're not getting you chasing dead code. We're not getting you chasing dead vulnerabilities as such, right? And it says, hey, like, seriously, it's not going to happen, right? It's not exploitable on modern 64-bit systems, right? Not probably fine, ruled out, move on, right? What you get at the end is, I guess, confirmed findings that your team can act on, all right? We try and filter the noise out. There's definitely exploitability verdict with evidence, and that's really, really important. And we give you that attack path. We show you untrusted input coming in and where it goes. And if you've asked for it, we give you a working proof of concept, an exploit code, and then secure patch suggestions. I think from a tooling perspective, this is pretty cool because it fits really well into model pipelines because of Serif, that we do everything in JSON reports so you can push it into issue trackers. We also have coverage tracking across runs, and the most recent push that we put in was full project history. So you can compare runs over time. And if you do this in a CI/CD pipeline, that's really useful. So we start off at 606 raw findings. We had 2 validated, but we had 1 that was really bad, and that was CVSS, and we got a POC for it as well. Great. Now, we are also looking at where we're going beyond static analysis. We've added a crash analysis. So you can feed Raptor a binary and the crash input and go from there, and it tries to work out what was going on. Really, really useful when you don't have the source code, especially for older legacy applications where maybe that's been lost. We are trying to get better at our fuzzing. We love fuzzing on the Raptor team, John, Gaddy, Michael, and I. Right, we really do, and we want to make it more usable and enjoyable for all. And I think pairing fuzzing with large language models is just chef's kiss. We want to do more OSS forensics, right? Again, we want to start looking at all your deleted commits, trace, tampered history, and so on. And we want to get better at our code understanding. All right. We really want to have a visual representation of your attack surface and all the data flows and so on. And that's the stuff we're working on. So who is Raptor for? Well, I guess all, really. People that are interested in finding bugs, people that want to leverage large language models for helping understand context, security teams, and anybody responsible for kind of fixing stuff. Developers, we do think that Raptor definitely has a use when it comes to running it on your own repo, and you do get actionable findings. And then researchers, help us find the bugs in open source projects that millions of people use, and let's try and give those open source maintainers lots of patches. And then finally, pen testers. Like, we're trying to build something for you as well. So that's the key thing. So where are we going to take it next? Lots. Like I said, we are trying to get it better to work in the full pipeline, purely from an agentic perspective, static analysis, leveraging all these tools and just giving you lots and lots of context back. We want to get better at web app scanning. The foundation is kind of there. We've got Playwright, we've got a crawler. It's very much alpha, but we are definitely trying to build it, and we would love help from the community. and far more language coverage. So at the moment, we're really strong on C, C++, Python, Java, and we're expanding to other languages. The key thing is we want it to be a community project. It's open source, like use it, break it, send a PR, like so many of you have done. Thank you so much. And the more people that find the weird bugs that John, Gaddy, and I have put in and help fix, great, everybody's happy. So yeah, the tooling was there. And I think we're in a very exciting time at the moment for finding bugs in a lot of code bases. And what large language models to me are giving me is the context, the telling me what I should really care about. And I think that's for me probably the most exciting part about bug hunting. So you don't often need a full-time vulnerability researcher, all right? Raptor can help you a lot. I'm not saying those people are going to disappear, not at all. But we want to try and help people find as many bugs as possible. So thanks very much. I hope you enjoyed this and look forward to people using Raptor and finding bugs.